Okay, so let's get started. So today I'm going to continue with the discussion on linear time invariant systems, and I'll go back a little bit and cover the section on zero input response because I went through that a bit fast, and I want to talk about real and complex responses separately. And then I'll talk about the system response to an arbitrary input function xt, and which will give us some insights into stability. We'll consider stability in a lot more detail when we talk about control theory. So here I'll just give some kind of intuitive understanding of stability, and then move on to transforms, just a brief introduction to transforms, and then really get into the Fourier series. And the Fourier series is sort of the building block for transforms. It's the most intuitive transform, and if you understand Fourier series, you understand Fourier transform. If you understand Fourier transform, you do Laplace, and then with Laplace you get to Z. And with Laplace and Z, you have all the tools you need to do control theory. So there is this whole progression that we'll start with the Fourier series today, and then the rest of the lectures, which will be probably until the end of next week, will be just on transforms. Okay, so let me start with the zero input response. So we have some arbitrary function, and using the functional notation, we can represent this essentially on the form. I'm just going to write down the short form of this, PD, okay, yt equals qd xt, where p and q are polynomials in D, where D is the differentiation operator. And I already wrote out the full form of this last time, so nothing new there. The interesting part here is that the polynomials in D are polynomials on functional forms rather than polynomials in variables that you've seen earlier. So but they still obey the same rules. In particular, you can factorize them as we normally do. To find the zero input response, and by zero input we actually mean that it's zero other than at the point zero itself. So after time zero there is no input, but at time zero we could have an impulse, and in fact we will have an impulse for there to be any response at all. And so this zero input response is given by setting PD yt equals 0, because the input is over here and that's 0. And that point, what we can do is we can factorize this, and the case we considered was when you can factorize this using distinct factors as d minus lambda 1, d minus lambda 2, etc., d minus lambda n equals, this is a polynomial in degree n. I think n is capital N is what I use, with lambda n equals 0, and then this leads to the what I call the characteristic modes, and this general solution is sigma I equals 1 through n ci e to the minus lambda I t, which is a set of complex exponentials because the lambdas belong to the complex plane. So this is a bunch, it's an additive sum of complex exponentials with some factors c sub I. Okay, so this is just reviewing quickly what we did last time. So the two things I want to point out here, the first is that this form is there only because it's a linear time invariant system. Okay, we're getting all this because it's LTI, so we're getting the sum because it's additive. Okay, each individual element over here is a possible solution, and the total solution is going to be the sum because of LTI. And the second thing is that these forms over here, e to the lambda I t, they look like those k e to the sigma plus j omega t that we looked at earlier, and in fact they are pretty much that. And it's I should be more careful, sigma plus j omega t. And so these are called the characteristic modes of the system. Okay, these are the, so if you kick that tray as I did last time, the sound it produces is characteristic of that. If I change it, if I tighten it or loosen it or something, then it's going to behave differently, and the response is going to be different based on what the system naturally is. Okay, so it's kind of, it's what's called a natural response. It's what the system is going to be doing. If you don't give it any additional input, you just give it some energy and you say, okay, do what you want, and that's what's going to happen. So if I leave the classroom, okay, whatever you're doing then, reading your mail, chatting, talking, reading your textbook, whatever is your natural response. Okay, it's not a forced response. Okay, and that's also called the zero input response. This is what you do when there's nobody looking. Okay, or at least when I'm not looking. That's your natural response. Yes.
Why do you have a negative sign for lambda?
Why do I have the negative? In the exponent there. Oh, sorry, I should take it back. Oops. Yeah, see, I take it. Yeah, sorry, because the roots are going to be d plus. Yeah. Yeah, sorry. I'm so used to thinking of exponent. Yeah, it is plus. It actually, the sign doesn't really matter actually, as you'll find out. Okay, so that, yeah, but it should be, to be consistent with this, it should be, yeah, sorry, my mistake. The one thing I should point out is that where do these CIs come from, right? I never tell you where the CIs come from. The way that it comes from is that actually, at the end of the day, they're going to come from the XTs. Because what's going to happen is at time 0, we're going to match the outputs. So the CIs depend on essentially y0, y dot 0, etc., y to the n 0, which in turn depend on the x, on the xt on the right hand side. So that's how we find what the CIs are. Okay, so I'm not going to go into that in too much detail. The reason is because the analysis of this kind of system, which is called the time domain analysis, is kind of finicky and not too much insight is there. And basically nobody really needs to do it or does it. It's just a building block in the step for us to get towards transforms. So it can be done. People have done it, but I'm not going to go too much into detail. But I do want to talk about what happens when you have a complex response. So let's just do a simple example of the real response. And for example, if you consider if you consider this one, d squared plus 5d plus 6 yt equals 0, for example, is going to be the an example of this where PD is this. Then this is d plus 1 times d plus 5 y equals 0, and this gives us the equation C1 e to the minus lambda 1, sorry, e to the minus t plus, right, what am I doing here? This is 1 plus 5, 3 plus 2. Okay, and that gives e to the minus 3t plus C2 e to the minus 2t equals is the response yt. Okay, so this is real. Okay, C1 and C2 are going to be reals, and the value we'll find will be from y dot and y dot 0 and y double dot 0 have to be given to you. And when you're given these two values, you can plug it back into these differential equations and figure out what the values of C1 and C2 are. And as I said, I'm not going to do that, but you can see that this is basically two reals. Let's just see what it looks like. C1 e to the minus 3t is exponential dropping off. It's a real exponential. It has no complex components. And it's going to drop off pretty fast, like this. And minus 2t is going to drop off as well, but less fast. So we have that, something like that. And then the sum of these is going to be an exponential as well. Okay, and again, it's going to drop off to 0. But it's the sum of these two things. So the sum of these two exponentials is going to drop off as well exponentially fast. So that's what it looks like over there. What happens when we have complex? This is the first new thing we'll talk about. Let's take the case where we have d squared plus 1 yt equals 0, and which we factorize as d plus j into d minus j yt equals 0. Okay, so here is where the first time we've seen where these lambda over here is complex. In fact, it's the simplest complex thing. It says j. Then what we get is that the natural response is going to be yt equals c1 e to the minus jt plus c2 e to the jt. Okay, so we have these two things. So how do we visualize this? And here the easiest thing to do is to simply replace this using the Euler's formula, right? You have minus jt and plus jt, and so let's just do that. So we get c1 cos minus t plus j sine minus t plus c2 cos t plus j sine t, right? And that's just expanding e to the minus jt as cos minus t plus j sine minus t, and e to jt as cos t plus j sine t. Now we know, or we should know, that cos minus t equals cos t. Oops. It's and then sine of minus t equals minus sine t. This is just the equations for the, so using this, we can expand this as being c1 cos t minus j sine t plus c2 cos t plus j sine t. And if you expand that again, we get yt equals c1 plus c2 cos t, okay, plus j c2 minus c1 sin t. Okay. So far so good. Nothing really great. All we've done is expanded by Euler's formula. But the interesting part is when this refers to not a mathematical formulation but a real system. Okay, when you have a real system of any kind, we know something about it, which is that there are no complex modes. In reality, there are no complex modes. We only have real modes. The imaginary J is imaginary in that sense. Okay, so any system, though we can represent it as a projection of a complex helix onto the real plane, in reality is going to have only real modes to it, right? So what we know is that this is going to be real, and this is also going to be real. Okay, this including the J is going to be real. Okay. So this is something we know. And so the two things we can assume we know about a physical system is that the response yt is going to be real and it's going to be causal. Okay, causal meaning it has no value. It is 0 before time 0. At time 0, sort of the Big Bang, the world began. Before that, nothing. So we know that yt is 0 before 0. Okay, we're not going to use that fact over here. We're going to use this fact over here. So let's just say C1 equals A plus JB, and it will turn out that the only way to get this to work is C2 equals A minus JB. Okay, and if you don't do it this way, then we're not going to get the fact that C1 plus C2 is real and C2 minus C1 is real. So we need to have, actually, am I doing this properly? C2 minus C1, or I think it should be, oh yeah, that's right, C2 minus C1 is going to be minus 2JB, and then you multiply by the J over there and you get plus 2. So C2 minus C1 is going to be, or J times C2 minus C1 is going to be real, right? This whole thing over here is going to be real only when the C2 minus C1 is going to have no real component. It's going to be pure complex, right? Only with a J. So given this, we can plug it in and find the values, but I'm going to note on this fact over here, which is that C1 and C2 are complex conjugates of each other by definition, right? We have some real part and some imaginary part, and the imaginary parts are exactly equal and opposite, okay? And we're getting this requirement because of the fact that we have this kind of form over here, and we're getting this form because we're getting essentially over here this notion that we have these two terms, minus jt plus jt, okay? And this comes from the fact that we have this plus j minus j, okay? So whenever we have this kind of form of equal and opposite plus j minus j, it's going to look like this over here. We're going to get complex conjugate coefficients for the for these terms in the real in the time domain, okay, over here yt. And we'll see this over and over again, that the responses, when they're complex, will be complex conjugate. Okay? Okay, because they're not conjugate, we don't get a real response. Okay? And so I just want to highlight this, and then when we talk about control theory, you'll see, again, there's a reason why this happens, but you'll see that whenever we see complex numbers, they'll occur in conjugate pairs. Okay? And the conjugate, that makes it somewhat easier to analyze what's going on. The interesting point over here from another perspective is that this whole thing is actually, it's a real sinusoidal, response. It's real because it's causal, because it's real, you know, we kind of define it to be real, but it's pure sinusoidal. There's no complex components to it. Once you put the C1 and C2 in this form, so the J's go away, and what we'll get is an oscillatory response. So what happens is you kick the system hard at 0, and it's just going to resonate, okay, or sorry, not resonate, vibrate with a pure oscillatory response over here, and it isn't decaying. Okay, there's no decaying component to it. It's just real sinusoidal over here. And so when this happens, well, it's like a guitar string. You have a guitar string, you pluck it, and it just it vibrates, pure oscillatory. Okay. And it may not, it's not a pure sinusoid. It could be, in fact, in this case, it's a sum of sinusoids. But in this idealized system, it doesn't decay over time. Once you pluck it, it keeps going forever. Okay. And what this means is that this equation over here is not a real system. Okay. It's a made-up system. So if you look at this system and say, oh, this can't actually exist, and that's why it looks like it's an eternal sinusoid for that reason. Okay, I've thrown a lot of things at you, so I'm going to stop now and just see, are there any questions? Yeah?
Could you explain again why C1 and C2 have to be complex
conjugates? Okay. I did a little bit of hand waving over there. What I'm saying is this. I have to come up with two numbers, C1 and C2, such that, which are complex, such that their sum is real and the difference is purely imaginary. Okay? Because this is multiplied by j over here. And if you don't do this, then yt will have some value j associated with it. But yt is real because it's a real system. Okay, if I have a real system and look at the observe what yt is at any point in time, because yt is some kind of amplitude, right? Some kind of amplitude. If I plug a guitar string, I don't have any complex amplitudes. I only have real amplitudes. So, but nevertheless, in the solution for the system, I have some complex quantity. So that quantity must be multiplied by some pure imaginary value here, such that it goes away, it becomes a negative number, essentially. Right? So I have to get rid of that complex part. Okay. This is only true because it's a physical system. If I were to give you a mathematical object, which says here's a mathematical object, go ahead and analyze it, then I can't tell you the complex conjugates. Then it's just, whatever it is, whatever the roots are. But because it's a real system, I can get this additional bit of information which tells me the roots are complex conjugates. So in other words, another way of looking at it is somebody tells you here are the characteristic modes of the system, okay, these are the characteristic modes. Then if you find that it's imaginary, one of them, then you'll say that's not a real system. Okay, that's not a physical system. Something else. I noticed that I'm kind of reusing the C1 and C2 perhaps more often than I should, because this one, these C's are not the same as those C's. Are they the same C's? Wait a minute. Yeah. Yeah, I should probably use. No, I take it back. Yeah, this should be something else. So this is. Yeah, I'm reusing those C1 and C2s a bit more than I should. But at any rate, some constants over here. These are the constants really. Am I doing it? No, they are the same. Okay, I'm sorry. I can't see that at that end of the board from here. But yeah, they are the same. Yeah, those are the C1 and C2 from these, which are these C1 and C2s as well. Okay.
So those C1 and C2 can be complex.
This one over here, this one has got to be real, because again, I'm claiming that this is a real system. Okay, if this is a real system, then C1 and C2 here must be real. When we have repeated roots like this, then we have this J coming in, okay? And that J, because here I don't have any J. If you notice, I have pure real response over here. Okay. Yeah?
On your lecture notes, you wrote down the final equation as the lecture response is 2a cosine t plus j 2b sine t.
That's, oops, yeah, that's a mistake, yeah. That J is definitely a typo, sorry. It should be 2a cos b plus 2b sine t. Yeah, this clearly it's a, that's definitely a mistake, sorry. I'd better fix that. Okay. Okay, and then the last thing, and I'll take a break, is when I talked about these repeated roots, or I guess I didn't talk about, your question? No, okay, the repeated roots, and I'll just give you the equation for that, and that's kind of, if we have repeated roots, because we can have that from the polynomial, roots of multiplicity R, then we have yt equals c1 e to the lambda t. So repeated roots, this is lambda, the root is lambda, and that means we have something like d minus lambda to the power r in the polynomial. Then we'll get c1 e to lambda t plus c2 t e to the lambda t plus cr t to the r minus 1 lambda t, sorry, e to the lambda t plus the other terms which correspond to the other roots over here. Okay, so that's what that looks like. I'm going to just switch order a little bit and talk about stability first, and then come back to the system response to xt, because actually we already have pretty much everything we need to discuss stability. So let me do that over here. Okay. So I'm going to just state, and then I'll show you in just a minute, prove, I guess, something about a LTI system, which is that the LTI system, the way it behaves is dependent on the roots of this equation over here. Okay, the PD yt, the roots of this PD yt equals 0, the roots of the characteristic equation, which correspond to the characteristic modes, which is what happens when you give it an impulse response, impulse input at time 0, determine essentially how the system is going to behave depending on these roots. Okay, and so when we look at the stability of a system, I haven't actually said what the system is. Okay, and just as a aside, when you talk about the system, we actually have in mind two different systems. One system is the uncontrolled system. So we have a system which is, we're just modeling it, we have no way to control it, and it's doing whatever it's doing. Okay, and the second system is the controlled system, where we're putting in some control input so that it has some proper behavior. For all purposes, stability response relates to the control system. Okay, so what is an example of a control system? Again, an example which maybe will make sense. Let's say that you're driving a car and you go over a pothole. Okay, there's a pothole, and so when the car goes over the pothole, there's a sudden sharp jerk. Okay, impulse input. Okay, and then after that, the car continues on. So that impulse, that sharp input, can be thought of as an impulse input to the system. And now we can think of the car having 2 or 3 different responses. And in your own experience, you probably experience these kinds of responses. If it's a car with a suspension that's very tight, very tight suspension, what will happen is you'll feel this big thump, okay? And you'll kind of feel it, and it'll kind of vibrate a little bit, and there will be a sharp jerk, but it'll kind of stop, okay? It'll be just this very sharp. On the other hand, if you have a big car or a truck or something like that, a really big old car, you won't have the sharp jerk, you'll have a response, but it'll kind of take a while for it to die down, okay? And eventually it will die down. Okay, so it's a control. What's happening is that your shock absorbers are essentially a control system. Okay, we can talk about the response, and we'll study the exact difference between these two mathematically in a little bit. But intuitively, what's going on is that we're given some input and we have some response. It really doesn't depend on the nature of the input. Okay, it doesn't really depend. It's input. It's some sharp input, but what the response is going to be characteristic of that system. Okay, if it's a big old car which has a lot of weight on it, it's going to have that smooth and slow response, no matter whether the pothole is one pothole or you have a bad road. Okay, it's going to have that smooth response all the time. Whereas a sports car is always going to be kind of jerky no matter what. So that's why I call it the natural response. And they all depend on the roots of this equation over here. And it falls into basically three categories. So these roots are of the form lambda, which belongs to complex. So it's a complex number. So it looks like sigma plus j omega. And just look at one root, this particular one. Let's say sigma is greater than 0. Then the root is going to look like e to sigma e to the j omega t. Now this is a helix. And if you note, if sigma is greater than 0, it's a helix that grows larger and larger over time, right? So what's happening is that we kind of have this helix that grows bigger and bigger, and this is going to be uncontrolled and bad system. That's your Tacoma-Narrows bridge, okay, where the modes are growing. The sigma is greater than 0. So anytime we have a root of this such that if any of the roots has a sigma greater than 0, we're going to have a system that is whose response yt is growing with time. Okay, that's bad. Okay, so it's unstable. Okay, so we call such a system unstable if any sigma greater than 0. So that's the first rule. If any sigma, it's unstable. Okay, so if all the sigmas are less than 0, we're in good shape because everything is decaying down exponentially fast. Okay, you get an input, it's going to go down, right? Yeah.
Yeah, at the very last line, you missed the coefficient of t for sigma.
Oh, sorry. Yeah, sigma t. Thank you. So if any sigma is greater than 0, we're going. If all sigmas are less than 0, then it's stable. Okay, because everything is going to die down. Because we have this strong e to the sort of minus something t forcing function. This is just oscillatory. That's just sinusoidal. Its magnitude doesn't change over time, right? It's just cos omega t plus j sin omega t, whose magnitude is always 1. It's a phasor of magnitude 1 rotating round and round, okay? But we're modulating it with e to the minus t, e to the minus something t, and the bigger sigma is, the faster it dies down. So what's happening in a sports car is sigma is very large and negative, okay? So it just goes right down, okay? Whereas in a Cadillac, okay, the sigma is small and negative, so it doesn't go right down. It takes a while to kind of glide down, okay? Now, if all the sigmas are 0, then what happens is we have basically everything neither positive nor negative. So this term essentially is 1. This term is just 1, right? So then everything depends on this e to the j omega t. If we have just one root, if you have one, to be more precise, if you have one, so if it's on the j-axis, okay, this is the real axis, this is the imaginary j-axis. If it's one root on the j-axis, we know it's going to be complex conjugate. So you're going to have two roots actually like so on the j-axis. Okay, they're going to be complex conjugate reflected about the real axis like that. If you have one root like this, then it's going to look like essentially like this one over here. C1 plus C2 cos t plus sin t. It's going to be oscillatory and never die down. Okay, so we call this marginally stable. Okay, it's not exceeding, it's not shrinking, it's just staying where it is. It just keeps oscillating round and round. Okay, like a guitar string. Okay, without any dampening, it'll be the guitar string. So if all sigma equals 0 and non-repeated, then it's going to be marginally stable. And if you get repeated roots which are also on the j-axis, then we get this, where did I put it? So this was this thing over here where we have the t e to the, so we have c1 e to the lambda t plus c2 t e to the lambda t plus, so when you get this one over here, the t term, that's growing with time, right? When you get repeated roots over here, you get growing with time. When you get growing with time, then at that point, we're going to have unbounded system. So remember, this one over here corresponds to d plus j, d minus j. So these are not repeated roots. These are just complex roots, right? When we have repeated roots, then we get the repeated complex roots, then we get two of these, one on top of each other, and then we're going to get the system that's unstable. So we have kind of 4 cases. All the sigmas greater than 0, or any sigma greater than 0 unstable. All sigmas are less than 0, it's stable. If all sigmas are 0 and we have non-repeated roots, it's marginally stable. And all sigmas is 0 and it's any repeated root, then we have unstable again. Okay, and so we can just take the system, express it in this form, PD equals 0, PDYT equals 0, compute the roots, and then immediately tell whether the system is stable or unstable or marginally stable just from that. So this modeling of the system as PDYT is extremely important. Okay, it determines what's going on. That's the, so again, the intuitive reasoning behind stability, and then we look at this in somewhat more detail. Okay, repeat this actually 2 more times, because this is really one of the, this is at the heart of control theory. How do we get this to work? Okay, so in short, what we want to do is to choose the system parameters such that all the sigmas are going to be less than 0. Okay, and that's what and the value of the place where sigmas is called a pole of the system, and so we want the poles to be placed in the left half of the complex plane. That's what's called pole placement. Okay, we'll come back to that. Okay, any questions about this? Yeah.
What if some are greater than 0 and some are less than 0?
If any sigma is greater than 0, it's unstable, because that's a mode.
Okay,
Yeah,
right.
if any sigma is greater than 0. Yeah. Any other questions? Okay, so moving on, I'm going to now talk about the response to the to a non-zero input. Yeah.
If all are 0 and 1 is less than 0?
If all are 0, right, it depends if it's repeated or not.
Except for 1?
Yeah, that's okay. If it's less than 0, just ignore it, because anyway that's going to die out.
Okay,
Right.
so just the remaining ones.
Yeah, the remaining ones, yeah. So we basically, yeah, we're looking at the ones that are possibly going to cause growth. So if it's repeated roots, then we're in trouble. If they're not repeated, then we're going to be marginally stable. So some modes will die out, other modes will persist. If you hit a piano key, for example, some harmonics will die out quickly, and some harmonics will sustain for a longer period of time. Okay, if one of them sustains forever, that's going to be on the j-axis. Okay, so stability. Let's look at the response to. So the equation that we have for a LTI system, not for any other system, LTI system is what's called total response equals 0 input response plus 0 state response. And that's not in the text. I'm just I don't want to put too much in there, but anyway. So this what we looked at is so far is 0 input response. Now we're going to look at what's called 0 state response. It means in the beginning of time we're assuming that the system is 0 state, and I'm not going to explain exactly what 0 state is now. We can define that precisely, but you can think of it as initial conditions are, there's no energy in the system. It's quiet. Nothing is happening. We're going to go through a little bit of mathematical, I won't say trickery, but a few steps that are a little bit that each step by itself is easy, but when you put it together, you get a very important and nice result. So I'm going to go through that. It's similar to the zero input response, so I'm going to go through that. And to do this, I'm going to use a new notation, which is this arrow over here, and let's call that leads to. And so we're saying this input leads to this output. Okay, and that's just the notation over here. So I'm saying if I give this input, remember I want to look at the response to some input xt.